consider my talk in the morning. It's also my last part of the series lectures. So in the morning, I have introduced what is the class-Lemma equation. It's given by a E equals G and R equals to R belongs to tensor space, and algebraic equation by R12, R13 plus R12, R23 plus R12, R23. It's called classical Lemma equation. Of course, in the morning, I just gave the definition. Classical Lemma equation is very important in the study of, I think, in several fields. It was first given by, the name was given by the reading the school in the last 80s, and in the study of some integral cerebral system through the way of inverse scaling method in the last 80s. Here, the Yang is the Chengming. Chengming Yang is the Chinese American physicist. He obtained the Nobel Prize in the last 50s. And Baxter is Australia physicist. And in fact, the classical Lemma equation is not, discovered by the Yang or Baxter. In fact, they found the quantum case. The quantum Lemma equation is when the Professor Yang found it around 1967 in the study of the quantum integral system. And here, Baxter is 1972 or 1973 in the study of the statistical physics. Okay. Anyway, and the quantum Lemma equation is also is very important in a series of in a lot of fields. And the classical Lemma equation can be regarded as the classical limit of the quantum Lemma equation. In fact, the relationship between the quantum and classical Lemma equation, just like the relationship between the Lie group and the Algebras. So in some things, the Algebras with the differentiation of the differential from the Lie group, we can get the algebra, and from the algebra we use the exponential map, we can get the Lie group. It's almost the same. It's also interesting from the analog, we can see in some things the classical Lemma equation study should be easier than the quantum case. But it was the quantum case which was the first discovered. Not like from the discovered history is from the difficult to the simple, but it's as the same as the study of the Lie group and the Algebras. It was the Lie group who was found by the Sophie Lie at first. Then, as a byproduct, the algebra was founded as the infinitesimal structure of the Lie group. But later, the algebra become an independent topic in the study. Okay, so the Yang classical and Yang Baxter is also the same. Of course, although the Yang classical Lemma equation is discovered by the former Soviet school in the last 80s, it's in the study of the metaphysics, and later it was founded. In fact, it already appeared in the mathematics. It's around last 40s. It was founded. It was founded just like the social bracket in the different geometry. And the classical Lemma equation is very popular, become a very popular topic since the last 80s due to its role in the study of the quantum group. In fact, from classical Lemma equation, we can get Lie algebra, the algebra. is the one kind of the from one equation we can get the a class of divisor, and from divisor we can get the condensation. We can get the so-called quantum group. So in some things, we give some solution by the Dune field and by Dune field study, we can get some structure of the quantum EQuaLS8 algebras. So the key point is we should give some solutions of classical Yamaha equation. Okay, and in the morning we also know when the G is finite dimensional, so the R can be write in a basis by a classical R matrix. Okay, so when it comes down into a linear map or linear transformation, okay, R, why, what kind of condition R should satisfy is equivalent to this one. So it's a very natural question. And the first answer was given by Smirnov. Yes. In 1983. These are no three persons, no one person. It's one name. Okay? And they prove. And the following two conditions. One, a constraint condition on the Lie algebra itself. G has a non-degenerate symmetry invariant Berlin form. Here, the invariant means B is Berlin form x, y, z equals to B x, y, z. This is a constraint condition for the Lie algebra itself. This condition is also makes sense in a lot of subjects. For example, for the semi-simple Lie algebra, we know this just the killing form satisfies this condition. And there are also some structures, some algebra Lie algebras satisfy this condition. It's also the name is, for such Lie algebra is called quadratical Lie algebras or self-dual Lie algebras. And they also appeared some study in the field theory. For example, in the confirmed field theory, they have the so-called construction. We need such conditions. And second, R is Q symmetry. Under these two conditions, the tensor form R is G equals to G. With the same matrix components, R should satisfy Rx, Ry equals to R, Rx, Y plus X, Ry. Okay. Okay, here you can see, under these two conditions, this Clausian equation, the tensor form, is equivalent to a linear form. And here, we have already seen in the morning, from here we can obtain the pre-Lie. We call it the operator form of Clausian equation. That's the reason why we call it the operator form of Clausian equation. Because under the two conditions, these two equations are equivalent. So this is the first operator form of the Clausian equation. It's given by the Smirnov. In his paper, the title of the paper is what is classical R matrix. Okay, and he said by this one we change the tensor form. As I explained in the morning, the tensor form is not easy to handle because it's in the tensor space. But here, I think it's very It's easily to understood. Okay, so that means we gave the first one. But please remember, this equation is equivalent to the Cauchy-Gamma equation under these two conditions. Okay, the R is skew symmetry, and they have a constraint for the Lie algebra itself. So, in particular for the condition 1, because for such Lie algebras, they are not enough. Many Lie algebras is without this property. So, a very natural question is whether we can delete this condition, and we should have a more general correspondence with some of the linear operator form to replace the tensor form. And the second approach is going by the following. The first approach is going by the Bertin-Sansky, and we have already seen it's very important. And as I also told in the morning, this is also called the Rota-Bus operator. But here we can see the Rota-Bus operator approach and the classical Gamma equation approach is totally different, totally independent. Here is totally from the study of mathematical physics, and the Rota-Bus operator is just from the pure math in the study of the probability and the combinatorics. So, but at this point, the two subjects is meet together. It's very interesting in the mathematics. Okay. And the second is given by Chengming. In the 1999. And in his paper, the title is "What Real a Classical R matrix is." So in some things you can see he gave some of the challenger to the Bertin-Sansky, but to my knowledge they are good friends. Maybe they just make some drop. Okay. Okay. And in the Bertin-Sansky work, he want to delete the first condition. And he noted for the tensor space, if the finite dimensional is equivalent on the side of G star to G. Okay. It's then, which means the theory is okay, in these things, for n R equal belong to the G, R satisfied if CYBE plus if and only if we still use the R by this correspondence, that usually is R A tensor B bracket equals to R A B. Here means because R is in the tensor space, G and T, A star, B star belong to the G star element. G star is the dual space of G, and this makes sense. So we also use the R, means a map from the G star to G. So here is G star and G of R is dual symmetry. The second condition should be K. Then satisfied. here is done is the G equal here is done is the dual representation or drum representation. It's called cold drum. Okay. The AD star is just the dual representation of the drum representation. It's also called the cold drum representation. So that means, okay, for the any element in the tensor space, it's just can be regarded as a linear map from G star to G. Notice here the R is a linear transformation from G to G, and here it's not a linear transformation but a linear map from the dual space to the G, and satisfy this condition. Okay. And notice because A star, B star belong to the G star, so R A star is in G and it's also in G. And here is the G and in G, and it makes sense to act on the G star and R. So the result is also in G. So this identity makes sense. So no problem. Of course, here we can see this theorem given by Chengming just delete cancel this definition, this construction. That means for any algebra, this makes sense. But R is still symmetry. And here we use the linear map to replace the tensor form of classical equation. So that means the classical equation just by this one. So this could work. So we can see it. Of course, this condition y is the pair. It's not this condition just means the G star G as representations of G. So that means from Chengming, if this is this, just reply with make the G star space with G. Makes the same. So from this one, we can see the simultaneous work is just a consequence of the Chengming. So that's the reason. Okay, so we give a very good result to replace the tensor form of classical by a linear form, by operator form. But the story is not stop here. That doesn't stop here. There are some more interesting facts. And Chengming found, okay, here, we can rewrite by the ADRX y minus ADRYX, right? AD is just the adjoint representation. And here is the adjoint representation. And here is co-adjoint representation. Okay? And then Chengming gave the following definition. Explanation. Give a Lie algebra and the representation of rho V. Rho is the action. And O operator is T from the V to G. It's called O operator. It's just by the TU, TV equals T rho TU epsilon V minus rho TV epsilon U for any UV. he replaced the adjoint representation and the co-adjoint representation by any representation. It's called the operator. So, by this one, of course, it makes sense. So in these things, the simultaneously work is just the operator associated to the adjoint representation, and the Cauchy-Mieter's work is just means is the operator associated to the co-adjoint representation. Of course, now there are many expectations are not satisfied with this notion. I think when the Cauchy-Mieter published his paper, he just called the operator means the O is the operator. That means operator. So many persons don't like this this notion, but because we should give enough credit to him, we still use this notion. Now there are many persons who call it generalized Robust-Buster or the relative Robust-Buster operator. Anyway, we still here keep the operator. And he said, in his work, he said, essentially, the all operator should be the essential of Clausian equation. He didn't explain why it's essential. He just gave the operator as a generation of Clausian equation. Okay? So a very natural question is, this only in a mind. Okay? Why whether an operator can give a solution of Clausian equation in tensor form? It's a very natural. Of course, it includes the Cauchy-Mieter work and simultaneous work on the components, but in his work, it's very natural whether we can give a solution from the operator form. If it's right, we can get not matter this one, but also this one. We can directly give some solutions of the tensor form without any other conditions. So that means we should unify the tensor form and outer form of Clausian equation. So that's what I did about I think 8 or 7 or 9 years ago. My work is give the unification of the tensor form and the outer form. That's one. So indeed, from all operator, we can get a solutions in tensor form of Clausian equation. Okay. From all operator, we can give the solution of EYB. Okay, in fact, the solution of EYB Clausian equation not in the G or V, but in some the big algebra. We noted the whole VG should V star tensor G, right? And this can be embedded in the G plus V star tensor G plus V star. That's right. For any element. So, so we should consider this one. And we can give the implicit components. For example, we give the V1, Vm is the basis of V, and E1, En the basis of G. So for any t equals to, for example, Tv, t can be right, t, Vi, T is okay. In fact, T can be right. VI star TVI. For any t from the V to T, we can write this one. Yeah. Then, conclusion. We need this. Only the okay. Then, for any t, t is an operator. If and only if the r equals t minus sigma t. Because t can be written the tensor form, the sigma t just change the order of the t tensor g. So that means here is sigma t is just the tvi tensor vi star. It's a solution. It's a skew symmetry solution of CYBE in G rho star. So that means, of course, the quick-reader gave the notion just as the generation. But here we prove if it's an operator, it's indeed give a solution of classical equation. In this big Lie algebra, it's just like what I mean is the direct sum of the Lie algebra and its representation by this one. So, and it's by the skew symmetry part of T as a tensor element. So that means from operator we indeed can give a solution of a classical equation in a big Lie algebra. So for the not only for the simultaneous work, construction or the quick work, we indeed can give some of the solutions in the tensor form directly by this one. So the next question is how to construct all operators. If we have enough operators, we can construct enough solutions, right? So next we should consider how to construct all operators. Then for this question, freely appear. So here we can see freely appeared very naturally. So why? So in order to obtain the operators, we can use the freely. So next we give the relationship between the freely O operator and CYBE. We can see from the operator we can get CYBE, and from operator we also can get freely. The first construction is that T equal to G is an O operator. Then on V, on the representation space, UV is rho TU x on V. So, from this very easy conclusion, we can see the pretty is just can be obtained from the operator directory. Here are operator, and this one is a pretty. This just on the representation space. We know that the so-called TU TV operator is just the rho TU on V minus rho TV on U, and this part. Okay, we can see this part is just operating. So it's a direct consequence. From this one you can see very easy. And another corollary is just given by, because the rotor bust RB of beta 0 in the morning we mentioned it's just a special Rx Ry equals to Rx y minus xry. It's just a special operator associated to the drum limitation. So by this construction, we can imply, okay, x tensor y, yes, it's just Rx y is operating. So in the morning, we will first give the construction of the predicate from the social intervals by the object form of class Lemma equation. It seems very strange, but from this one, it's quite normal. Okay, because in fact the root operator of with 0 is just a special operator, and the operator can get a natural predicate. Okay, so we give the not direct proof, but a very natural proof. So that's as a direct consequence of this construction. So from this one, we can see all predicate is a very natural structure, underlying structure of operators. And the operator also can give the solution of Lemma equation, right? So, but we have some other more results. Some other more results is we can see that this condition here we only give the representation space of V. Whether we can use this to give some the construction of predicate on G itself as the commutator of the predicate is a very next question. So we should see if V and the G is the same, we should use some the inner transform inner isomorphism. So we should consider the invertible case. The invertible, we can see, in fact, the operator is not new result, no new notion. In fact, when T is invertible and T is an operator, if and only if T minus 1, the inverse, is a one-to cycle. In the morning, we have the definition of one-to cycle. One-to cycle is very common, very known result. In fact, the operator is nothing. It's not very new. It's just the inverse of one-to cycle. However, when it's not invertible, we cannot get the study the results involving the operator from the study of one-to cycle. So I think the mathematics is so wonderful, so interesting. Even in the case of invertible, it's the same, but if generalized to non-invertible, we can know some new results. It's very interesting. Okay, so then we can get the directly theorem. A Lie algebra has a completable predicate. Algebra If and only if G has an invertible O operator. Because in the morning, under the invertible operator, we can very easy. In particular, dot relief. Identity. Again, identity is an O operator associated to R. The representation R is just given by the pre-lead, the less than multiplication operators. So why we introduce pre-lead? First, pre-lead appeared as a consequence of the operator. On the other hand, if we want to construct the operator, okay, we introduce the product, the algebra pre-lead, just means we use by the introduction of the new algebra structure pre-lead, we can construct let the identity be a natural O operator. So that means in order that we want to construct some of the operators, we change the problem to construct some algebra structures. Such as the algebra structures just give some the natural construction of the operator. So that's our idea. So that means we change the study from the classical solution to the study of the operator. And from the study of operator, we change to algebra structures. Then, by this one, and with the operator construction, we can get from 3D we can directly get solutions of CYBE. Give a pre-D, and R equals to EI into EI star minus EI star into EI. The basis is EI EN. A solution of CYBE in G R star. Oh, sorry, A. Use A. It's commutator. A star. So that means from a pre-lead, we can directly give a solution of Young equation with the uniform form by this pre-lead. A solution in this diagram. We notice this diagram comes from the implicit of the structure of the pre-lead structure. Without pre-lead, this cannot exist. So that is why we can do the construction of the pre-lead. So pre-lead here appeared in the study of the Young equation. Not only, but also from pre-lead we can construct a real solution of Young equation in tensor form. So that's the main result. So in this case, the pre-lead is very important. So give a pre-lead, we can construct this result. So a natural question is open question. We have already studied this question, have been studying this question for many years. From this one, what is the explicit structure? Wow. So that means how to construct the condensed this solution. Okay. So that's the main, the main relation between the Clausius equation and R and the predicate. In a summary, we give the such research framework. Okay. In a summary, so we give the CYBE, the tensor form, and it's by the operator form. Okay, of CYBE. We construct the unification of these two forms. We know most of the application is in the tensor form. With the unification, we can, by the study, many results of operator form can apply to the related topics. On the other hand, the tensor form is not easy to generalize, but the operator form is quite easy because it's the operator form you can add some additional terms. And with this unification, we can, through the generation of the operator form, can get the generation of the tensor form. So we have done a lot of work along this approach. Moreover, this one is, there are some algebraic structures, like predicate. One side, from operator form, we can get some algebraic structures, and algebraic structures also can give some examples of the operator form. Then, give some solutions directly from the algebraic structures. This is the predicate, the rows in this study. And with the generation of this framework of research, in the past several years, we get a lot of results. If you are interested, you can see my works in the recent years about this approach. Okay. Okay, so this is the main introduction to the brief introduction to the study of the predicate and the operator and the Clausius equation. So that means the predicate indeed gave the very important results related to the Clausius equation. So, at the end of my talk, I will give some new interpretation of the lattice symmetry. Okay. We can see. You know, in the geometric interpretation of the lattice symmetry means geometry. It's just the nabla, the affine connection with the tensor with zero flatness. Okay. Now we give algebraic interpretation. We can see what is the algebraic interpretation. In fact, we give a class matrix. R matrix means R, we can see Rx, Ry equals to R, Rx, Y plus X, Ry. Okay. Give a basis. So Rei equals to Rij, Ej, yeah. And R is called R11, R12, R11, R12. Right. Then we know the predicate is nothing, just X, Y, Ei, Ej, Eim, En, tensor En equals to R, En equals to, according to this one, is sigma R M J E J E N. What does it mean? In some things, the algebraic inversion of left symmetry, because it's the left symmetry of the product oscillator, and it's just like the Lie bracket left twice by a classical R matrix. So we just give some the point of view. So this doesn't mean that's like, so of course if we define EIN equals to EM REN, the same, this one is defined indeed right symmetry. So that means the right symmetry of the oscillator is thus the Lie bracket right twice the class of R matrix. So in this sense, the predicate in algebraic, the implication, it can be regarded as the Lie bracket left twice the class of R matrix, and the right is right twice the class of R matrix in this sense. And the geometric is just the flatness of one connection. Okay, so this is some of the observation. So that means we give the implication of the left symmetry in the both and both the geometric and the algebraic. So up to now, we gave I should finish my introduction to the 3D. Of course, 3D there are also many other topics involving the study of 3D. For example, you might know we have another class involving the study of some more generalized node algebras. That means we can put the study of 3D in a big framework with the other kind of the algebras, because it's involving the too many definitions. If you are interested, you can check my note and some of the related study. Of course, the 3D also have other appeared in other fields. To my knowledge, when someone want to study some structures involving some of the new representations from the double space or some of the two big space with intervening some of the representations, maybe, just maybe, it's quite possible the 3D will appear. It's my experience. Of course, I hope, because I used this chance to give the brief introduction to 3D, I hope more and more persons can be interested to this subject. Okay, thank you very much.